Welcome, folks. Video here discussing the concept of reduced row echelon form. So a little bit of motivation here. Last time we saw that we could make a system of equations simpler by using equation operations. So as it turns out, only the coefficients of our system of equations really mattered there, and not the variable. So we'll develop a method of manipulating those coefficients with some notation. We'll see how manipulating our equations with equation operations gives us has sort of an equivalent interpretation in this new notation, and then we'll talk about this special type of form called reduced row echelon form. Okay, so we'll start off with some notation here. Many of you have seen a matrix before, but we'll define it here. An M by N matrix is a rectangular layout of numbers. These numbers are generally over the field of complex numbers, although most often we'll only deal with real numbers. Our matrix has M rows and N columns. Now our numbering convention is that the first row is at the top and the first column is at the left, and these rows and columns are numbered from top to bottom, 1 to M, and from left to right, 1 to N respectively. So generally speaking, we use capital letters to denote a matrix, and we'll use square brackets in this course to indicate elements of a matrix. So here's an example. Here's a matrix B. We can see it has 3 rows and 4 columns. So again, with 3 rows and 4 columns, we say that the matrix is 3 by 4. The element in the second row and third column, B23, is -6. And the element in the third row and second column, B32, is 4. Okay, so another definition, a definition of a column vector. A column vector of size M is an ordered list of M numbers in order vertically, which we typically just refer to as a vector. Okay, so in text, vectors are generally denoted with a boldface. We usually write them with a hat. When we're writing, we'll use square brackets to indicate vector entries, just like we do with matrix entries. And again, we almost exclusively use column vectors. So a couple special column vectors. Here's the 0 vector of size M. The 0 vector of size M is a vector with M entries where every entry is 0. The 0 vector size M. So we can use these matrices and vectors to represent a system of linear equations. So here is the system of linear equations that we talked about in our last video, right? The system with M equations, N unknowns. We define the coefficient matrix A as a matrix of coefficients. And here we just pick off each element of x1 through xn in the first through mth equation. Okay, so A11, A12 is the element in the first row, second column, out to A1n, the first row, nth column, and then all the way down to A sub m1, the mth row, first column, over to A sub mn, the mth row, nth column. Okay, similarly, we can define the vector of constants, right? The vector of constants is the vector containing m entries, right? Say size m. And we see that we get the entries 1 through m by just picking off the constants on the right-hand side. We can similarly define a vector called the solution vector. The solution vector is a vector of size n, which is x1 to xn. Okay, armed with these two vectors and the matrix A, we can describe this linear system of equations. So if A is a coefficient matrix and B is a system of, and B is a vector of constants, we can write LS of A comma B is a compact notation for the matrix representation of this linear system. So here's an example. We'll go ahead and have a look at this, this system of linear equations here and identify the matrix representation. Now, I won't go through this in its gory detail, but we can see there are 3 equations in 5 unknowns. So we expect the matrix A to have size 3 by 5, and we expect the vector of constants B to be a vector R3. Okay, so again, because there are 3 equations in 5 unknowns, we expect A to have size 3 by 5. And because there are 3 equations, we expect our vector of constants to be size 3. So I'll let you work through picking off all of those coefficients to construct A and B. Okay, another definition. If we have such a system of linear equations, M equations, in n variables, and the matrix A is a coefficient matrix, and the vector B is the vector of constants, we can identify the augmented matrix of this system by writing a new matrix where we just append the vector B to the end of the matrix A. Okay, again, this is called the augmented matrix of the system. Okay, often we omit this vertical line, and we can see that because B had M elements to begin with, that our new matrix still has M rows, and appending one additional column to our matrix makes it have n plus 1 columns. So this augmented matrix, A augmented by B, represents the linear system of equations with coefficient matrix A and vector of constants B. Okay, it's a good opportunity to discuss one of the neat features of this book is a number of archetypes that we'll sort of continue to refer back to. So here's an example where we're going to write the augmented matrix referring to archetype A. So we can see this system of linear equations in archetype A has 3 equations and 3 unknowns. So we expect the augmented matrix to have size 3 by 4. So we see that the first column of this augmented matrix is just the first column of A, 1, 2, 1. The second column is the second column of A, minus 1, 1, 1. And the third column is the third column of A, 2, 1, 0. Now, of course, the fourth column is the vector of constants B, which in this case is 1, 3, 5. Now, as it turns out, the equation operations that we discussed last time are exactly doing operations on this matrix that's augmented. So those end up being called row operations. So we know that equation operations yield equivalent systems, so we'll define the following row operations that transform a matrix into another matrix of the same size. So the first row operation is to swap the location of any 2 rows. The second row operation is to multiply each entry of a row by a non-zero constant. And the third row operation is to multiply the entry of one row by a constant, add it to another row, leave the first row the same, and replace the second by the new values. So it's good to use some consistent notation here. So let's talk about notation for these different row operations. So the equation swapping any 2 rows, we'll use the notation Ri swaps with row Rj for row I swaps with row j. If we want to multiply Each entry of a particular row by a non-zero constant, we'll denote that by alpha row I. And if we'd like to multiply the entry of one row by a constant, adding it to another row, giving us a new second row, we'll denote that by alpha row I plus row j. And again, this gives us a new row j, leaving row I alone. So another definition, we say that two matrices are row equivalent if one can be obtained from another by a sequence of these row operations. Okay, so as an example, here we have two matrices A and B, which end up being row equivalent. So to see that these two matrices are row equivalent, it looks like we can maybe swap row 1 and row 3, and then use some row operations to get a new row 2. So in this first row operation, we've swapped row 1 and row 3. And in the second row operation, we've taken minus 2 times our new row 1, right? Row 1 is the former row 3, but now it's row 1. And we've added that to row 2 to give us a new row 2, leaving row 1 alone. And it looks like there's a small typo here. This 7 should be a 6, obviously. Sorry about that typo. Okay, so we can see that you can get from one matrix to the other with a sequence of row operations. So again, we say that these two matrices are row equivalent. And I'll point out that this sequence of row operations is always is reversible. That turns out to always be true, right? So if we want to go backward here, we could take, for instance, 2 times row 1 to give us a new 2 times row 1 plus row 2 to give us a new row 2. And then, of course, swapping back row 1 and row 2 gives us the original equation. So this is always true that if you can get from A to B, you can get from B back to A again too, right? So row operations are always reversible. Okay, so why we care is because if A and B are augmented matrices that are row equivalent, it turns out that the related systems of linear equations are equivalent systems. Okay, so remember what that means. Equivalent systems are systems that have the same set of solutions. Okay, so doing these row operations on an augmented matrix, right? That's where you take the coefficient matrix and slap on the vector of constants to the end, doesn't change the set of solutions at all. Okay, so the proof is in the text, but the idea of the proof is that if A represents some linear system and B represents another linear system, that each row operation on the matrix is the same as an equation operation on the linear system, right? So we know that equation operations don't change sets of solutions. So similarly, row operations on augmented matrices don't change sets of solutions. Okay, so in order to explore this, let's go ahead and have a look at an example. So here is an example where we'll go ahead and solve this system of 3 linear equations and 3 unknowns through a sequence of row operations on the augmented matrix. Okay, so here, again, we would pick off the constants 1, 2, 1 for the first row of A, 1, 3, 3 for the second row of A, and 2, 6, 5 for the third row of A, and then slap on our vector of constants 4, 5, 6 to augment. So here we see A augmented by B. And the equation operations we saw last time, where we took minus 2 times the first equation plus the third equation to give us a new third equation, here is represented by the row operation. Minus 2 times row 1 plus row 3 gives us a new row 3. And similarly, the second one is minus row 1 plus row 2 gives us a new row 2. Okay, so again, equivalent matrices because we've reached one matrix from the other by a system of row operations. Equivalent matrices have the same set of solutions. So we can go ahead and write the equivalent linear system here that results from this new augmented matrix. Okay, as you can see, this is exactly the linear system that we got last time, and we saw how we could use back substitution to solve for x2 and x1 once we know that x3 is 4. Okay, so here again is the unique solution to this system of linear equations. x1 equals 2, x2 equals 3, x3 equals 4. And we've obtained this by a sequence of row operations on the augmented matrix. Okay, so it turns out there's a method to the madness here, and the best way to do this is to manipulate an augmented matrix until it's in its reduced row echelon form. As it turns out, that's going to be the best way to identify a set of solutions to a system of linear equations. So the definition of reduced row echelon form is sort of complicated. There are 4 sort of buttons that you have to check in order to identify that a matrix is in its reduced row echelon form. So the first, any row where every entry is 0 is at the bottom of our matrix. Second, the leftmost non-zero entry in every row is 1. Third, the leftmost entry in a particular row being 1 is the only non-zero entry in that column. And last, we have this IJ notation, but basically what it means is when you run into one of these entries where there's a 1, it sort of has this descending order. Okay, so I'll make a couple comments about these entries. Okay, so we say that the first one in each row is called a leading 1. Okay, so when we talk about these leftmost non-zero entries in a row, those are called the leading 1s. Each column that has a leading 1 is called a pivot column, right? So when we talk about the leftmost entry being the only non-zero entry in its column, every pivot column has a 1 in its leftmost row spot and all zeros up above it and below it. And then qualification 4 can be sort of described in terms of these leading 1s and pivot columns. No leading 1 can be left of a leading 1 above it. Okay, and for any m by n matrix, we can partition our column indices depending on whether they are a pivot column or not. So such a m by n matrix may have r pivot columns, and such an m by n matrix, since it has n minus r non-pivot columns, has a set f1 to fn minus r that represent the non-pivot columns. So this is better illustrated with an example here in just a moment. Okay, so here is an example of a matrix that is in reduced row echelon form. Okay, we see that this matrix has 5 rows and 8 columns, right? So it's 5 by 8. We see that our matrix has R equals 3 pivot columns, right? Those pivot columns are the columns corresponding to a leftmost entry in a particular row of 1 with zeros above and below it. So our partition then of pivot columns are columns 1, 5, and 6 are our pivot columns D1, D2, and D3. Okay, similarly, our non-pivot columns, the set F that's the partition, is again 2, 3, 4, 7, and 8. Okay, so we can always do this given any matrix in its reduced row echelon form. Identify the number of pivot columns R, and then partition those column indices into the pivot columns and the non-pivot columns. Okay, here's an example of a matrix that's not in reduced row echelon form. So we'll go through a number of reasons why it's not in reduced row echelon form. The first is that we have a row of zeros that's not at the bottom. The second is that we have a leftmost entry in this second row that's not a 1, right? So that violates item number 2. Also, we have an entry in a pivot column that's non-zero, right? So that 7 in the first row and 6 column violates rule number 3. And the fourth has to do with this rule number 4, where we have the leftmost entry, in this case row 4, column 2, and compare that to the leftmost entry in row 2, column 4, right? So we don't have this I less than S and J less than T. Okay, so we'd have to swap those around in order to have this in a non-violation of number 4. Okay, so a couple of theorems about reduced row echelon form. So it turns out that every matrix A has a reduced row echelon form, and moreover, that reduced row echelon form is unique. Okay, so this is a pretty cool deal, actually. Let me give you some sort of take-home messages for these two theorems. The first theorem, REMEF, right? You can always find a row equivalent matrix that's in reduced row echelon form, and this is known as an existence theorem. And then theorem RREFU, right, is a uniqueness theorem that says if you have two reduced row echelon form matrices that are row equivalent to the same matrix A, then they're the same matrix. So again, this first theorem is that every matrix has a reduced row echelon form. That's a statement of existence. And the second theorem is a statement of uniqueness, right? There's only one such reduced row echelon form. This is super special. As it turns out, mathematicians are often interested in existence and uniqueness, and it gives us sort of a strategy for identifying the solution of a system of linear equations. So if we have a system of linear equations represented by coefficient matrix A and vector of constants B, our strategy is to augment and then find the reduced row echelon form. We've seen how this reduced row echelon form introduces a bunch of zeros and ones. We like zeros and ones in systems of linear equations. We know that row operations leave systems of equations equivalent. So that reduced row echelon form, once interpreted, ought to tell us something about our system of linear equations. So here's an example. The matrix the system of linear equations associated with archetype B has this form. We can go ahead and write the augmented matrix and find the reduced row echelon form. So this can be done by hand. This can also be done using technology, and we'll go ahead and explore that a little bit using Sage, and I recommend you do that on the worksheet. In any case, this new matrix is pretty simple, and we can quickly interpret our results here. So the new system of linear equations, represented by this augmented matrix in its reduced row echelon form, has solution x1 equals -3, x2 equals 5, and x3 equals 2. So that's about as simple as it gets, and that's the solution to this system. Okay, so we'll simply represent that unique solution as -3, 5, 2. Going back really quickly to our other example, we see that A is a 3x3 matrix, right? 3 equations and 3 unknowns, and R has 3 pivot columns, right? The reduced row echelon form of the augmented matrix has 3 pivot columns. We can play this game with archetype A also, and if we play this game with archetype A, augmenting, reducing to row echelon form, we see that, okay, so similarly, our reduced row echelon form has a row of zeros at the bottom. Okay, so again here, and I didn't do this on last example, and maybe I'll go back now and mention this. In this case, we can see that A, our matrix of coefficients is 3 by 3, but in this case there are only 2 pivot columns, R equals 2 pivot columns. So in this case we see that the set of solutions can be represented by an infinite number of solutions, where x1 is 3 minus a and x2 is 2 plus a, for x3 equals to any value of a. Okay, so again here, the number of variables 3 and 2 pivots, right, leaving 1 free variable. One more example sort of illustrating a system of equations with no solution. So again, we can augment our matrix of coefficients by our vector of constants, reduced to row echelon form. And we can see that there's something sort of interesting going on here. We can see that this last row of our augmented matrix in reduced row echelon form is associated with an equation that is nonsense, right? 0x1 plus 0x2 plus 0x3 plus 0x4 equals 1. So we conclude that this system of equations has no solution. Okay, as it turns out, there's a very special relationship between pivot columns, the augmented matrix, and whether an equation has solutions or not. And we'll see that next time. So that's all for now on our reduced row echelon form. Thanks for your attention, and we'll see you next time.